continuous function. Right? Integrate, you get limit as a approaches infinity of the natural log of x on the interval of 1 to a. I don't have to worry about absolutes because the only numbers that are going in there are non-negative. So this would become the limit as a approaches infinity of the natural log of a. Natural log of a minus the natural log of 1, but natural log of 1 is 0, so it's irrelevant. All right, so I can leave that be. All right. Now, a natural log function is an increasing function throughout its domain. It never stops increasing. All right, so this has a limit equal to infinity. So we're talking about a situation that diverges. All right. So when we formally kind of define this in the p-series test at the bottom, we'll reflect back to this and say, okay, when the p-value is equal to 1, we got a divergent situation. All right. So let's see what happens when the p-value is equal to 2. All right. In terms of the setup, not much difference, but we will end up with a completely different antiderivative. All right, so I need the antiderivative of, well, this is really the same as saying x to the negative second, right? So it would be negative x to the negative first over the interval of 1 to a. Plug in the a. We're looking at, I'll write it as a fraction, just make it a little bit nicer. Negative 1 over a minus a negative, so plus, you plug in a 1 for that, you're just getting a 1. Alright. So when you apply the limit here, you get a clean answer. You get just the number 1, so this one converges. Alright, so you get anything that's not infinite. So basically something that's real, that's not infinite, is going to indicate that it converges. Again, not saying that it converges to this number, just it is an indicator of convergence. Alright, now the 1/2, similar idea. So we're looking at, again, this is better represented in slightly different form. And so it become 2x to the 1/2. Over the interval of 1 to a. So that would be the same as 2 times the square root of a, I'll write as a radical instead of a fractional exponent, minus 2. This part is forever increasing. Right? If it's forever, a radical function, same idea as kind of a natural log. It never actually levels off. It just slows down its rate of increase. All right? So this is going to increase forever. So therefore, we are looking at a situation that diverges. All right, because it's going to infinity. I suppose I should write infinity in there somewhere. All right, yeah, so we have some possibilities, and that's actually one of them. If the p-value is negative, if p is, I'll say less than or equal to 0, so I'll include the 0, even though it's not negative, obviously. But in these cases, you're not dealing with a p-series. Right, so I'll just give it a quick example of that. If you had something like the sum of 1 over, I guess it doesn't matter. I'll just do n to the negative third power. That's the same as the sum of just n to the third power, right? And if I had the sum of 1 over n to the 0th power, well, that's just 1 over 1. That's just 1. So if you manipulate them at all, you'd see that they don't follow the correct format of 1 over n to the p power. All right. So it has to be a non-negative, or actually a positive value of p. So then our possibilities are really narrowing themselves down to, if you look at the examples, we have cases where it's 1 or more, and you have cases where it's less than 1. All right. So in the case of 1, we have a divergent situation. In the case of 1/2, we have a divergent situation. If we had a 3/4 or a 3/8, you would have a divergent situation. I won't bore you with that. But basically, it's telling us that if we have any p-value in between 0 and 1, then it's going to diverge. All right. So fractional p-values all the way up to and including the 1, you would have a diverging situation. The other possibility is a case where p is equal to 2, maybe 3, maybe 10, maybe 40. In all of those cases, the series will converge. So any p-value that is greater than 1, the series will converge. So then when you see the example below, it just got a whole lot easier, because you don't have to use an integral test for this, comparison test or anything like that. What we have to do is manipulate it algebraically a little bit. Write the radical n as n to the 1/2 power. Keep the base, add your exponents. And you can see that this is now a p-series. But it follows the correct format, 1 over n to the p power. All right? So we can now state confidently that it converges by the p-series test, PST. Specifically, here you do have to go a little bit more, specifically because your p-value is greater than 1.